Welcome! In this video, you will learn basics of probabilities, learn about sample space diagrams, expected values, and relative frequencies. Probability is chance of something happening. For example, rolling of a fair dice produces range of possible values between 1 and 6. Although this action produces the number between 1 and 6 for certain, but we couldn't actually tell which number will show up for any given roll of the dice. All the possible values shown on the dice is called the outcomes. A particular outcomes that are of interest are called the events. For example, getting 1 on a dice can be one event, or getting an odd number on a dice could be another event. Probability is full of jargons. It is the language of probability that makes it often confusing for some to understand the question. It is really important to pay attention to the language in order to understand the question, which then ultimately helps you to solve the problem. We often use the word like random or fair to denote that the events are equally likely. For example, we could say that dice is fair, which means that all the numbers on the dice is equally likely. Or we may say that a person is randomly chosen from the class, which means each person is equally likely to be picked. Probability of an outcome to an event is measure of how likely that the outcome will happen. When the events are equally likely, it is given by dividing the number of ways the event can occur by the total number of possible outcomes. For example, a fair dice has 6 possible outcomes, as it can land on any of the number equally when rolled, but there is only 1 2 on a dice. Therefore, probability of getting a 2 when a fair dice is rolled is given by dividing the total event 1 by the total outcome 6. In order to write this in more concise way, we often use shorthand notation, and we write P of A is equal to 1 over 6, where P stands for the probability of, A denotes the event assigned, and everything enclosed by the bracket is the description of the event. On this occasion, A denotes that you get 2 when dice is rolled, and it's equal to probability 1 over 6. Probabilities can be written as a fraction or can be expressed as a decimal as well as percentages. However, the value of the probability will always be between 0 and 1. Therefore, we can also view the probability as a scale going from 0 to 1. When the value of the probability is 0, we say that the event is impossible to occur. For example, when dice is rolled, getting a 7 on a dice is impossible as there are no 7s on a dice. So the probability of this happening is precisely 0. When the value of the probability is 1, we say that the event is certain. For example, when rolling a dice, probability of getting a number between 1 and 6 inclusive is certain. When the value of the probability is a half, the event is described as equally likely or even chance. For example, getting an odd number on a dice is equally likely scenario, as there are 3 odd numbers which are 1, 3 and 5 out of the total 6 outcomes. As the probability value gets closer to 1 from half, events are more likely to occur. But if the value goes closer to 0, that means events become less likely to occur. Suppose you have 2 pears, 3 apples, and 4 lemons in a trolley. If you were allowed to choose one of the items at random, then what is the probability of choosing a pear, or apple, or lemon, or a banana? There are totals of 10 fruits in the trolley, and only 2 of them are pears. So the probability of choosing a pear is just 2 out of 10. However, this can be simplified down to 1 over 5, as 2 can divide 2 and 10 both. When working with probability, it is often not necessary to simplify the fraction to the lowest term or change the number to decimal form unless stated by the question. So avoid temptation to express your answer in decimal form, as it can introduce rounding errors into your answer. Furthermore, there are 3 apples in the trolley, so therefore the probability of getting apple will be 3 out of 10. Similarly, getting lemon is 5 out of 10, but this can be simplified down to 1 over 2. However, there are no bananas in the trolley, so getting a banana from a trolley is 0 out of 10, which is equal to 0. These results can be illustrated in probability scale too. We first need to divide the probability scale in units of tenths. In the exam, you can roughly scale this one out, and we don't have to be super accurate on this, but make sure they are fairly equally spaced on the number line. Since 5/10 is equivalent to half, the probability of getting a lemon is equally likely event, and we cross the middle of the scale. And if you move towards 1, the events are more likely. And if you move towards the left, the events are less likely. And the probability of getting an apple is 3/10. So it's less likely event than the lemons, so will be roughly over here. The probability of getting a pear is 1/5, which is equivalent to 2/10, and it is even more less likely than the apple. So we put the mark here. And finally, there are no bananas in the trolley, so getting them will be impossible event. So we'll put a cross on a 0. When two things are happening at once, for example, flipping two coins at the same time, it is much easier to work out the probability if you list all the outcomes in certain logical order or use something called sample space diagrams. If two fair coins are tossed at the same time, there are 4 possible scenarios. It is possible that both coins show heads, or coin 1 shows head and coin 2 shows tail, or another way around, coin 1 shows tail and coin 2 shows head. And finally, they could both also show tails. Each of these scenarios are called sample points. When the coin is fair, each of these sample points are equally likely events. So chances of any one of these is occurring is 1/4. A full list of sample points is called the sample space, and diagram showing the sample space is called the sample space diagram. And in this situation, events can be a collection of one or more sample points. For example, getting heads on both coin can be one event, or getting head in one coin and tail in the other can be another event. Only one occasion out of total 4 that you can get heads on both coins. Since the coin is fair, all the outcomes are equally likely events. Therefore, probability getting 2 heads when 2 fair coins are tossed is 1/4. Similarly, getting 2 tails is also 1/4 because there is only one event when both shows of tails. However, there are 2 occasions when the heads and tails shows up. You can have the heads in the first coin and tails in the second, or you can have the tails in the first coin and heads in the other. So the probability of getting head and a tail is 2/4, which is also equivalent to 1/2. If you are interested in getting heads in the first coin and tails in the second, then there is only one way that this can happen. So the probability of getting head in the first coin and the tail in the second is just 1/4. There are 2 occasions when coins show the same side. Therefore, the probability of coins showing the same side is 2/4, which is also equivalent to 1/2. From the diagram, we can see that there are 2 ways of getting exactly one head. Therefore, probability of getting exactly one head is 2/4, which is also equivalent to half. When the question says at least one head, this will include sample points showing 2 heads as well as one head. So there are 3 ways this can happen. Therefore, probability of getting at least one head is 3/4. Let's look at another example. 2 fair spinners are spun and their scores are added together. Spinner A is divided into 3 sections numbered 1 to 3. Spinner B is divided into 5 sections numbered 1 to 5. Our job is to first draw a sample space diagram to show all the possible outcomes, and in part B we need to find the probability of scoring at least 7. So let's start with part A. So we want to draw the sample space diagram for these 2 spinners. Spinner A gives the outcomes 1, 2 and 3, and spinner B gives the outcomes of 1, 2, 3, 4 and 5. Going across the table, the first entry 2 is given by adding 1 from the spinner A and 1 from the spinner B. And 3 is given by adding 1 from spinner A and 2 from spinner B. And similarly, 4 is given by adding 1 from spinner A and 3 from spinner B. Continuing this, we are able to fill up all the possible outcomes given by these 2 spinners. Part B of the question asks for the probability of scoring at least 7. Since the spinners are fair, all the outcomes in the table is equally likely. There are a total of 15 outcomes. All of them are equally likely and 3 of them have the score 7 or more. So therefore the probability of getting at least 7 is 3 out of 15. You can estimate probability using the result of the experiment or from what we already know has happened. The estimate is called the relative frequency, and it is given by dividing the number of times that the event has happened by the total number of trials in the experiment. A trial in this case is basically simple action that generates some outcomes. For example, it could be simple action of rolling of a dice. An experiment is a collection of trial. For example, your experiment may consist of 10 throws of a dice, in which case it gives total of 10 outcomes from 10 trials, and that's equivalent to one experiment. Suppose you have this spinner and want to find out whether it is fair. How can you check this out? One of the simplest ways to check this is to carry out some experiment and calculate their relative frequencies. To start with, you can estimate the number of times the event will happen by working out the expected frequencies. Expected frequency is given by multiplying the number of times the experiment is done by the probability of the event happening. Say we spin the spinner 30 times. If the spinner is fair, theoretical probability of landing on blue, red and green is exactly 1/3. To find the expected frequency, we can multiply the probability by the total number of trials, which is 30 in this case. And if you do that, it gives you exactly 10 observations for each color. However, even if we spin the fair spinner, it is unlikely to show that exactly 10 observations for all the colors due to the natural variation. Nevertheless, if the spinner is fair, observation from our experiment should be close to the expected value of 10. If the spinner is unfair, then we should see a large difference between what's expected and what's observed from the experiment. Let's say you get the following result from the trial, which is shown by the observed frequency row. The relative frequency of the spinner landing on blue is given by dividing the number of times the spinner lands on blue, which is the same as the observed frequency, by the total number of trials. This gives 0.3. Similarly, the relative frequency for red is given by dividing 10 by 30 and divide 11 by 30 to give the relative frequency for the green. Since the relative frequency is close to the theoretical probability, we can say that the spinner is fair based on the given observation. The relative frequency is the estimate for the theoretical probability. Given that the spinner is fair, this estimate improves as you increase the number of trials. If, however, the trial shows this observation, which is given by the observed frequency rows here, then according to the relative frequency, the red is most likely to occur and blue is least likely to occur. So the spinner is biased towards red. However, in order to get more accurate picture of this, you may have to trial more times before drawing this conclusion. Will thinks his dice is biased. He throws the dice 300 times. The table shows this result. In part A, how many times should each number come up if the dice is fair? In part B, we need to find out the relative frequency of each score. And in part C, we need to find out if we think that the dice is fair and give reasons for your answer. Now you can pause the video and try this question for yourself, and then we can check this together. In part A, we want to find out how many times each number should come up if the dice is fair. If the dice is fair, then the probability of getting each number is 1/6. The expected frequency of the dice is given by multiplying the number of times the experiment done with the probability of that event happening. Calculating this gives us 50 for all the scores. So this tells us that if the dice is fair and rolled 300 times, we expect to see 50 observations for each score. In part B, we need to find the relative frequency for each score. Note that the relative frequency is the number of times the event happened in the experiment divided by the total number of trials in the experiment. In this experiment, there are 300 trials and score 1 was observed 50 times. So the relative frequency is given by dividing 50 by 300, which is equal to 0.167 to 3 decimal places. Similarly, score of 2 was observed 47 times, and dividing it by 300 gives us 0.157, correct to 3 decimal place. Continuing this, we can find the relative frequencies of all the scores. And this should always add up to 1 as well, since all the probability adds up to 1. In part C, we need to think if the dice is fair and give the reasons for the answer. If the dice is fair, the theoretical probability of getting any of this score would be 1/6. And from the table, we can see that the calculated relative frequency is close to the value 1/6 for all the scores. Therefore, it strongly suggests that the dice is fair. If you find this video useful for you, please click like. If you think someone else can benefit from it, please share. And if you want to hear from me again, please do not forget to subscribe to my channel. Thanks for watching. Be sure to try the exercises to test your knowledge. I'll see you in the next part.